Welcome to our lecture online, and now the next so many examples are going to be about what we call thin lenses. And there's a reason why we call them thin lenses, because if they're not thin, if they're thick, then the equation becomes quite a bit more complicated. So to simplify things a little bit here, we just talk about thin lenses, which is typically the kind of lenses we're dealing with in optics. All right, the first thin lens is the converging lens as opposed to the diverging lens, which means that if rays of light shine through a converging lens, they will converge on the other side. Matter of fact, if the lines are parallel to the normal, they will converge at the focal point on the other side of the lens. And in this case, we can then say that the converging lens has a positive focal length, and in this lens, the focal length is 25 centimeters, means the distance from there to there is 25 centimeters. Of course, the lens is symmetric on both sides in this case, since we drew it symmetrically, and so there'll be a focal point on both sides of the lens. The observer with lens problems is always behind the lens. So we put the object in front of the lens and the observer is behind the lens. And so if the image appears on this side, the same side as the observer, if the light shines through the lens, they converge to a single point on the other side of the lens, we have ourselves a real image. If something else happens, then we will not have a real image, we'll have a virtual image, and we'll see some examples of that. But the first example, we're going to put the object here at a distance quite far away, 100 centimeters away from the lens. And so that's kind of a special case. Let's find out where the image appears graphically. Just like with mirrors, we draw the first line here, the first ray, parallel to the normal until it hits the lens. And since it's a converging lens, it will bend towards the focal point and continue on through the focal point like that and onward. So that's ray number one. The second ray you draw through the focal point, and you take the focal point in front of the lens right here, because if it's a positive focal length, you will draw that ray through the focal point in front of the lens. So we draw the ray like this until it hits the lens, and then it will then diverge and continue parallel to the normal right here. And this is ray number two, and of course where the two rays meet like that, that's where the image will appear. And let's so draw the image right here. There's the image. And then this here would be the S prime, which means the distance to the image. And we'll figure out in just a moment how big that is. Notice that with converging lenses, if you put the object very far away, that means that the image will form very close to the focal point. The closer the object comes to the lens, the farther away the image will form. We'll see that in the next several examples. All right, now mathematically, we're going to try and find out what the distance to the image is. And of course, we're going to use this equation right here, S prime. S prime represents the distance to the image. So S prime is equal to S times F over S minus F. S is the object distance, F is the focal length. So S was 100 centimeters. Focal length 25, that would be 100 minus 25, and so it's equal to 2,500 divided by 75, and let's see here, that looks like about 33.3 if I'm not mistaken. Let's find out. 75, and sure enough, so about 33 centimeters. All right. What does that tell us? Well, it tells us that the image is 33 centimeters further behind the lens, so that looks about right. If this is 25 centimeters, that's 33. The fact that it's positive means that it's a real image. It happens to be behind the lens. The rays converge to a single point, so everything points to it being a real image. So I is real. Okay, next we want to find the magnification of that image. So M is equal to minus S prime over S. So minus S would be 33 divided by, S prime divided by 100. And that looks like it's minus 1/3, which means the size of the image is 1/3 the original object. So here's the object, there's the image to be 1/3 the size. Negative means that it's inverted or upside down, so the image is inverted. And there's all the answers that we were looking for. We realized the distance to the image from the lens, and it's 33 centimeters behind the lens. I is real because we have a positive image distance. The magnification is 1/3 the original size. Negative means that's upside down or inverted. And that's how you do that problem. The next example, we're going to start moving the object closer to the lens and see what happens.